Today I'm going to introduce Making BFT Protocols Really Adaptive, which is published in IPDPS. There are many BFT research out there. When you actually type the Byzantine fault tolerance or Byzantine consensus, you can find really lots of work. In fact, when you type the district consensus, which is more general term, you can find more than 30 million papers in the Google Scholar. The important thing is that they are all different. For example, different user cases, different scenarios, different deployment environment, different fault model, different configurations, different network model. More importantly, different trade-off. For example, between robustness versus performance and consistency versus availability. So therefore, we can conclude that there is no one-size-fits-all BFT. Here is a quote from the high-pressure fabric. Decades of research on consensus protocols have shown there is no such one-size-fits-all solution. But as a researcher, we can throw a question like this. Despite the no one-size-fits-all property of the BFT protocols, can you take advantage of the benefits of each protocol? The answer is yes. How to do that? By switching the BFT protocols at runtime, depending on the situation. For example, when everything is fine, we can use the GGBA, which is the most representative speculative protocol of the BFT family. But when there is fault, we can switch to the PBFT protocols. For example, when there is a Byzantine client or network fault or client contention, switching BFT at runtime is not new. The paper called the next 700 BFT protocols, which is published in EuroSys 2010 and as well as the IEEE TOCS 2015, and that paper introduced abstract, which represents abortable state motion replication. In abstract framework, they provide a mechanism for composing multiple BFT protocol instances, and each instance is tailored to specific system conditions and optimized. And each BFT instance does not interfere with each other at all, which means that the protocols can be combined in a modular way. And the most important property of the abstract framework, they suggest aborting running BFT and switching to the other BFT protocol if something goes wrong. For example, GGBA is the common case and PBFT at fault. And they define new novel concepts formally. For example, abortability, abstract composition protocol called ACP, and abstract composability theorem. And those concepts serves as a cornerstone for building abortable BFT system. Here is the typical architecture of adaptive BFT. The first phase is execution, which is literally executes user requests. And when there is fault, the replicas can abort the currently running protocol, and then they select a new protocol to switch, and then switch to that protocol. And after switching, the new protocol needs to get a initial state from the previously running protocol. And this phase is called recovery and state transfer. But the most important part is selection here. And selection can be divided into two categories. The first one is static selection, which means that protocol orders are fixed before deployment. For example, in the paper, the next 700 BFT protocol, the ellipse system suggests that this order: quorum, chain, PBFT, quorum, chain, PBFT, and those sequences. And second one is dynamic selection, which means that protocol orders are dynamically changing depending on the situations. So this is the contribution of this paper. This paper introduced ADAPT, the first adaptive BFD system with dynamic switching method that evaluates protocols at runtime using machine learning predictions. And they also devise new mathematical formulas for calculating evaluation scores to select the best fit protocol. And they also adapt to show that it outperforms other BFD protocols under varying system conditions. So, how to dynamically select a BFD protocol? Let's see the idea in a high level. The first phase is to monitor the system state. For instance, number of clients, fault, message sizes, and this information is used as a training data set for building machine learning prediction model. And second one is evaluate each protocol at runtime using machine learning predictions. More specifically, it calculates evaluation score of each protocol, and then it switches to that protocol having the highest evaluation score. And they also consider user preferences, which means that user can provide their preferred characteristics of BFD protocol. For example, does the protocol can tolerate Byzantine client? Adaptive architecture. Adaptive architecture consists of three parts. The first part is BFTS. BFTS is just a set of BFT protocol libraries supporting observability. And event system, ES. ES monitors system state and collect impact factor. Impact factor means that it's a kind of performance metric which can impact the performance of the BFT protocol. And it sends an event notification of impact factor periodically to QCS. QCS means quality control system. And QCS evaluates each protocol and determine when and which protocol to switch to using machine learning prediction. And the most critical part is the QCS evaluation process. And this process calculates a score for each protocol. And if the score exceeds some certain threshold, then switching to the protocol occurs. And there are two core evaluation metrics in QCS. The first one is key characteristic indicators, or shortly KCI. KCI represents static properties of BFT protocol and is defined by the BFT designer choice. For example, does the protocol can tolerate Byzantine client, or does the protocol have speculative execution, or does the protocol need IP multicast? And second metric is key performance indicators, or shortly KPI. KPI represents dynamic properties of BFT protocol, and it is calculated by runtime prediction mechanism. The example of KPIs include throughput, latency, and capacity. Throughput and latency, the concept that we all know of. The capacity here means that the maximum number of clients that a protocol tolerates. The goal of the QCS is to find the best fit protocol among n competing protocols. The leftmost term represents the most preferred protocol, and the protocol has the highest evaluation score E. Then how to calculate matrix E? Matrix E is calculated by the product of KCI matrix C and the KPI matrix P. The product sign of C and P is a Adamar product, which resulting matrix is calculated by multiplying elements at the same position of each matrix. KCI matrix C has the following expression. Let's break down piece by piece. Leftmost term is the final resulting form. In this case, the matrix represents that the user prefers PBFT and Digibat and quorum. And 1 over A is used to exclude protocols that do not match user preferences in matrix U here, along with the outmost bracket, which is integer value operator. And matrix A represents static characteristics of each protocol. Here, spec means speculation, BIJ means does the protocol tolerate Byzantine clients, and IP means does the protocol use IP multicast. And the union operator with an upper dot means that it has all the elements in each row. And EN matrix is a unit matrix which its elements are all ones. And U means user preference matrix. In this case, user prefers biz and IP property than spec. Then let's take a look at KPI matrix P. Leftmost matrix P has the following resulting matrix like this. In this case, P shows that most performant protocol at the moment is quorum, of which each evaluation score is 7. Matrix B represents performance metrics of each protocol, and this matrix is the main target of machine learning prediction technique. Here, relation between B and B to the plus minus is to reflect some value tendency. For example, for throughput, higher value means better, while for latency, higher value means bad. So to make a balance between values in the same mathematical formula, some normalization mechanism is applied here, as you can see. Matrix V is usually defined weight by KPI. In this case, matrix V shows that user gave more weight to throughput. Matrix W is used to adjust user preferences to heuristics, which we will explain next slide. This is summary of how to calculate evaluation matrix E. And this is a sample calculation with whole processes. An interesting point is heuristics. Heuristics are used to adjust a system behavior in exceptional cases. In fact, it adjusts user preference using commonly regarded rules. Here are two heuristic rules defined by the authors. First, H1 states that when concurrent clients are few, latency becomes more important than throughput and capacity. Second one states that under high contention, capacity and throughput become significantly more critical than latency. And heuristic is denoted by matrix W in calculating matrix P. And this is a process of building prediction model for KPI matrix. Event system monitors external system state and output to QCS periodically with the following form, containing system state, KPI item, and its value. And this output is used as a training dataset for building prediction model function F. And the goal is to find parametric values that allow the prediction function to make the most accurate predictions. And the prediction function take impact factor as an input and output prediction value. Here KPI value in matrix B. Because protocol switching is basically collaborative task, therefore it must also be Byzantine resilient. Each replica independently executes an evaluation process algorithm and agrees on the result. Here the result is about whether switching or not using PBFT protocol internally. Evaluation environment and methods. They used cluster of 25 64-bit Xeon machines with 2 GB of memory running Ubuntu operating system, and is deployed on EmuLab. EmuLab is a research purpose distributed system testbed, and they used 100 Mbps bandwidth. And they used 4 machines for 4 replicas and 20 machines for varying clients. And they choose their target application as Redis key value store. And they state that Redis key value store is the most realistic and appropriate application for their purpose. And they use A/B benchmark. Here A means request size and B means reply size, both in a kilobyte unit. And computing prediction is like that. They used support vector regression as a prediction method with the radial basis kernel, shortly RBK, and that is provided by live SVM library. And they choose their parameters of the function using 5-fold cross validation. And they use 500 records with the following form: number of clients, request size, response size, throughput, latency, and capacity. And they used 85% for the training data set and 50% for the test set. Now, before proceeding, let me describe some protocols used in the evaluation part. The first one is quorum. Quorum represents theoretical minimum latency among BFD protocols due to a simple one-phase message pattern. And it works well in contention-free, non-faulty condition. And second one is a chain protocol, which represents theoretical highest throughput due to low MAC operation. And it works well in contention-free, no network bottlenecks, and no non-faulty condition. And third one is ring. And ring exhibit less throughput than chain in normal case, and it works well even under network bottleneck, because every replica can be a sequencer and tail, which is opposed to the chain case. And fourth one is Jijiba, which is the most representative speculative BFD protocol. And fourth one is PBFD, which represents the most robust among the used protocol here. And first evaluation is about protocol selection at runtime. Here we can see that as the number of clients increased, the selected protocol changed. We can see that in the 0-1 benchmark scenario, when the number of clients is low, the protocol quorum is selected at the very first. But when the number of clients increased, the Jijiba protocol is selected. Interesting point here is that when there is a faulty replica, the PBFT is always chosen. We can see that from this evaluation that adapt selects the best fit protocol dynamically under varying system condition. Second evaluation is about performance comparison. Here we can see that adaptive is compared with various BFD protocols such as PBFT, Jijiba, Quorum, Ring, Chain, Ellip. Under varying workloads, we can see that Adapt actually outperforms than others by selecting the best fit protocol at runtime. And third, the evaluation is about switching cost. Here we can see simply that Adapt exhibits negligible switching cost of almost about 20 milliseconds with no faults, but it shows higher cost about 90 milliseconds with faults, but it is still tolerable. So to conclude, this paper introduces Adapt, the first adaptive abortive BFD system with dynamic switching method at runtime using machine learning predictions. And their evaluation demonstrates that Adapt outperforms others protocols under most conditions, especially dynamic workloads.